Okay, well, let's start off this by explaining this equation. Because one thing it has the value g, the universal gravitational constant. It needs a little bit of explaining. So, F is force, m is the mass of object 1, m is the mass of object 2, and d is the distance between the centers of these two objects. So from the center mass of this object to the center mass of this object is a certain distance, which is then squared, times a conversion factor, if you will, or a constant that corrects for the fact that we chose as human beings to use kilograms to measure mass and meters to measure distance and newtons to measure force, so this makes it work for those units. And it's a very small value. G is 6.67 times 10 to the negative 11th. And sorry for the weird units. That's what makes it work. So let's just think of it this way. Okay, so here is the force of gravity equals M1, M2. Now, if we take M2, let me erase M2. We take M2 and we make it larger. If M2 gets larger, so that's the mass of U, well, what that's going to do is it's going to make the force larger. Oops. The force is going to be larger. And the same thing would have been true if I had done that to M1. If you double the mass of either object, you'll double the force of gravitation between them. Cut the mass of either one of them in half, you'll cut the force between them. So there's a direct proportion. This shouldn't be an equal sign. There's a direct proportion between the product of the two masses and the amount of force involved. But if you look, distance is an inverse function. It's in the denominator. So what that means is force is also it is inversely proportional to the square of the distances between the two objects. So in other words, if the distance gets 2 times bigger, so I'm going to make the distance 2 times bigger. If the distance gets 2 times bigger, now I'm dividing by 1 over the square of that distance. So in that case, force gets not 2 times, but since it's squared, if this is 2 times bigger, 2 squared is 4, the force will get 4 times smaller. Similarly, if we find that the distance between the two object centers gets smaller by a factor of 2, the force of gravitation between them will get stronger by a factor of 4, because we are dealing with a squared function. Alright, well, let's just try applying this here then. Okay, here's how much I weigh on the surface of the Earth, 945 newtons. The question is, how much would I weigh on top of a building so high I am 4 times further away? In other words, I'm going to look at this relationship here. It's not going to be 4 times weaker. Since I'm further away, it's going to be weaker, but it's not going to be 4 times weaker. It's going to be 4 squared times weaker. So, in other words, it's going to end up being 1 over 4 squared times weaker. In other words, it's going to be 1/16 of what it was. So if I was 945, I'd say 945 divided by 16, that's going to give me 59.1 newtons. So I'm not using this equation here because I don't know what the distance is and I don't know what the masses are. I'm taking advantage of the fact that the force of gravity is inversely proportional to the square of the distance. Quadruple the distance, you cut the force by a factor of 16. Let's look at the next one. Suppose I weigh the same amount when I went to bed, but for some strange reason the Earth shrank so small during the night it was only 1/10 its radius. Now that means I am 10 times closer. My center mass is 10 times closer to its mass. So therefore the force of gravity is going to get stronger. But it's an inverse relationship. So if I get closer, it gets stronger, but it's an inverse squared relationship. So I will not be 10 times stronger. The force of gravity will be 10 squared times stronger, or 100 times stronger. So I'll take 945 newtons. Then I'll multiply it by a factor of 100, which will give me 945 and 2 zeros newtons. Okay, let's keep going here. Alright, here's how much I weigh on Earth. I changed my weight a little bit here. Alright, how much would I weigh on a planet that had the same radius? In other words, the I'm leaving this right here is going to stay the same. However, it only has half the mass, so I'm cutting the mass in half. If you cut the mass in half, you will cut the force in half. So all I have to do is say 654 newtons, and I'm going to cut it in half, because that's what happens if the Earth has half that much mass, in which case, let me look, I got it written down here somewhere. Half of that is 327 newtons. Alright, another one of these. Here's how much I weigh on Earth, how much I weigh on a planet that has the same mass, but the radius was 3 times bigger. That means I'm 3 times farther away, so gravity's going to get stronger. It's not going to get 3 times stronger, it's going to get 3 square times, or it will be 1/9 of what it was before. So I'll say 746 newtons over 9, and that's going to give me 82.9 newtons. Let's keep going. What have we got here now? Here's how much my climber has this mass, weighs this many pounds, which is this many newtons. How much would she, oh look at that girls, how much would she weigh on the summit of Mount Everest, this far above the center of the Earth? It has this mass. Now, you know what? Some of this information may be extraneous. Your job is not to throw everything into an equation, like throwing fruit into a blender to make a smoothie. You're just going to say, look, I see I have M1, M2, distance, and I was asked to find weight is the force of gravity. So I'm going to use the equation, the force of gravity equals G M1, M2, over d squared. Now let's just substitute these in. I'm looking for the force of gravity. That's how much she's going to weigh. G, let's see, I believe it's 6.11 times 10 to the negative 11th. Am I right? No, it's 6.67. I'm such an idiot. Alright. 6.67 times 10 to the negative 11th. That is a correction factor. That's going to correct it so that kilograms and meters is going to give me an answer in newtons. One way of thinking about this number here, if I took 1 kilogram of matter and placed it 1 meter away from another kilogram of matter, the force of gravity between them would be this many newtons. Alright, well anyway, so now what I'm going to say is times M1, which is 65 kilograms, times M2, which is 5.98 times 10 to the 24th kilograms, divided by, don't forget to square it, the square of 6,386,850 meters squared. Now, what that's going to give me then is the force of gravity equals 635 newtons. So notice, at sea level, you weigh 637, and at the top of Mount Everest, you're 2 newtons less. Because you're farther from the center of the Earth, you know what? Your weight goes down. 2 newtons, though, is not a whole lot. It's like half a pound. These are realistic values, by the way, people. I'm not making this stuff up. Alright, let's try another one. Let's see. I know I have an M1, and I have an M2, and I have a D. So I want to know is how strong is the force of gravity between me and the car? All objects pull on all other objects with gravitation, including me and my car. Let's just see how hard my car pulls on me. So I'm still, like last time, I'm looking for the force of gravity between 2 objects. It's going to be equal to 6.67 times 10 to the negative 11th, that's big G, times M1, which is 55 kilograms, times M2, which is 1,234 kilograms, considerably smaller than the Earth, I might point out, divided by the square of the distance between their centers. And when I run those numbers through my calculator, being careful to use my EE key and being careful to use my square button key, what I find is that the force of gravity between myself and the car is a whopping 5.03 times 10 to the -7th newtons. It's small, but it's there, and it is measurable. Okay. Now here's the mass of the moon. Here's the distance. Let's see. If you're standing on you're standing on the surface of the moon, you'd be this far away from its center. Here's your mass. How much would I weigh standing on the moon? Now remember, before we found I weigh about 637. Let's see, at 65. So I'd be pretty close to this on Earth, which is about 143 pounds. So let's see what I'd be on the moon. So again, it's how much I weigh. So I'm just going to say the force of gravity equals 6.67. You know, these are getting kind of redundant. I don't know what my problem is. Why am I always asking to solve for that? Times M1, we'll make that U, 66 kilogram, times M2, which is the mass of the moon, 7.34 times 10 to the 22nd, divided by, don't forget, it's by the square of the distance between their centers. So that's going to be, I'll put this in parentheses, 1.74 times 10 to the 6th squared. And now when I enter all that into my calculator, there's really no algebra involved here. What I'll find is 106 newtons, which is about 6 times less than I weighed on the Earth. You notice that's what I weighed on Earth, and here's what I weigh on the moon. Alright, welcome to the back side of your homework. What we want to find here is how much upward force does the moon exert on me when it passes overhead. The moon is an object, I'm an object, there's a force of gravity between us. Let's just calculate how much it is. Once again, I want to know what the force of gravity is. So I take the value of G, which is 6.67 times 10 to the -11th times M1. Let's make your mass be M1, 58 kilograms, times the mass of the moon, which is right here. So I'm going to say 7.34 times 10 to the 22nd. And now what I have to do is I have to divide by the square of the distance between our centers. So here's how far you're standing above the center of the moon. So that's the distance. We'll ignore your height. Alright, so that gives us then is 3.86 times 10 to the 8th, and don't forget you have to square that whole thing. So when you do this, what you'll find then is the force of gravity between yourself and the moon, between this person and the moon, is 0.0019 newtons. Not that strong, but let's try a different object. And don't forget, you aren't necessarily lighter because it's also pulling up on the Earth. But now look what we've got. Let's look at the sun. The sun's bigger. Let's see if it pulls harder. It is farther away. I wonder which is going to be a bigger factor. So, what we've got is, we wanted the force of gravity exerted on this person by the sun equals G. G is 6.67 times 10 to the -11th times M1. M1 is the person's mass, which is 58 kilograms, times M2, which is going to be a little bit on the large side, 1.99 times 10 to the 30th. Good golly. And I have to divide by the distance between myself and the center of the moon, center of the sun, which is 1.50 times 10 to the 11th. Now I'm going to substitute all these values in, and I'm going to calculate for the force of gravity. And what I find is the force of gravity equals, the sun pulls up, I'm at 0.0 342 newtons. Look how much harder the sun pulls on me than the moon. Wow. Who knew? Alright, let's keep going here. Newton knew how to find the mass of the Earth. He just didn't have a way of measuring a little g, a big G rather. So here's how we do it. Okay. If you take 1 kilogram of mass, that's M1, and you position it away from the Earth, so basically what we've got here is M1 is going to be 1 kilogram mass times M2, which is the mass of the world, is equal to the distance between the centers squared, which is 6.38 times 10 to the 6th, and we're going to square that whole expression, times big G, which is 6.67 times 10 to the negative 11th. And all of that equals the pull of gravity on that 1 kilogram mass. Well, that 1 kilogram mass is pulled down with 9.8 newtons. So I need to solve this equation for M2. What that means is I need to multiply both sides by 6.8 times 10 to the 6th squared, and then I need to divide by 1, and then I need to divide by 6.67 times to the negative 11th. And when I do, what I find, since I'm dividing by 6.67 times to the negative 11, and when you divide by a very small number, you get a very large number, what we find then is that the mass of the Earth is 5.98 times 10 to the, hang on, I believe it's the 24th, yep, to the 24th kilograms. Actually, that one just locked in my brain, you know what I mean? Okay, let's keep going here. Oh, it's the Romeo and Juliet problem. Alright, let's see what we got here. The first thing we want to know is we're going to try to use the universal law of gravitation to find the force acting on Romeo. So I want to know, what is the force of gravity that is attracting Romeo towards Juliet? Well, really, Juliet's not really what M2 is going to be. What M2 is going to be is the space station, because that's going to exert a much larger force on Romeo. So we're going to say 6.67 times 10 to the negative 11th, and now we're going to multiply that by M1, which is 68. And then we're going to multiply that by M2, that's the mass of the spaceship pulling on Romeo, well, they're pulling on each other, and it's 4.58 times 10 to the 5th, and those two masses are pulling on each other, and we need to know how far apart the masses are, and let's see, he's 25 meters away from the center mass of the spaceship. So I'm going to say 25 meters squared. Now all I had to do to find the force of gravity acting on Romeo is just multiply this, 6.67 times 10 to the negative 11, using my EE key, times 68 kilograms, that's the mass of Romeo, times 5.98 times 10 to the 5th, again using my EE key, and then I have to divide it by the square of 25, because that's the distance between them. What I get then is that the force of gravity between Romeo and the spaceship containing the balcony and Juliet is 3.32 times 10 to the negative 6 newtons. Small, but there. And if there's a force, there is acceleration. So therefore, let's calculate his acceleration using the second law. Well, acceleration, if you recall, goes up with force and down with mass. So therefore, the force of gravity acting on the astronaut is 3.32 times 10 to the negative 6th. And I got that from right here, and so I just calculated, divided by the mass of Romeo, which is 68 kilograms, and that's going to give me an acceleration of only 4.9 times 10 to the negative 8 meters per second But I am going to find that Romeo is speeding up. So now what I want to do is I want to figure out how long will it take Romeo to travel at 10 meters to get to Juliet. So let me see, equals 1/2 at squared. So d equals 1/2 at squared. The distance is 10 meters. Half of a, let's see, so I'm going to say 1/2 of a, and a is 4.9 times 10 to the negative 5th, no, 10 to the negative 8th, times t squared, and I don't know what that is. So now what we have to do is we're going to say, well, let's turn this into a number. So what's 1/2 of 4.9 times 10 to the 8th? Turns out that is equal to, let's just squeeze it in down below here if we can. So that means that 10 also equals, let's see, 2.45 times 10 to the negative 8th times t squared. Well, I want to get t by itself, so I'm going to divide both sides by this. So I'm going to have 10 divided by 2.45 times 10 to the negative 8th equals t squared. But I don't want to know what t squared is, I want to know what t is, so what I'm going to do is I'm going to take the square root of both sides. Take the square root of this side, I'm going to take the square root of this side. And therefore I'll know what t is. T equals 20,200 seconds. You know what? True love can wait that long. That's not that long. Okay. I hope you enjoyed it. I did. Bye.